Welcome to this explainer. Today we are unlocking what is honestly one of the most powerful toolkits in all of mathematics. We're going to explore the fascinating, kind of hidden symmetry between exponential growth and logarithms. Think about it. If you've ever watched how a viral outbreak spreads, or how a brand new car loses a chunk of its value the second you drive it off the lot, or even how populations explode, you're watching exponential functions in action. But to actually understand and calculate these massive, rapid changes, we need a special decoder ring. And that, my friends, is exactly where logarithms step in.
Here's our quick roadmap for today's session. We're starting off with the ancestor problem, then we'll break down what logarithms actually are, move into the laws of logarithms, talk through exponential graphs, and wrap the whole thing up with some really cool real-world applications.
All right, part 1, the ancestor problem, or as I like to think of it, exponential growth in reverse. This is literally the perfect starting point because it takes a big, abstract math concept and grounds it in something incredibly relatable, our own human family history. So, try this thought experiment for a second. You have 2 parents, right? And each of them has 2 parents, giving you 4 grandparents. Now let's keep going backward in time. Assuming there's roughly 1 generation every 30 years, and that all your ancestors were totally different people, how many direct ancestors did you have living back in the years 1700? It sounds like it should be a simple counting problem, but it actually hides a massive mathematical explosion.
Just think about how incredibly fast these numbers scale up. 30 years ago, that's 1 generation back, you had 2 ancestors. 60 years ago, 2 generations, you had 4. By the time we go back 120 years, which is 4 generations, you're already at 16 direct ancestors. The pattern here is super striking. For every 30-year jump back, the number of ancestors doubles. It's a classic geometric sequence. We're essentially taking a base of 2 and raising it to a power based on the number of generations. So to find our ancestors 300 years ago, which gets us to roughly the year 1700, we're looking 10 generations back. 2 to the power of 10? That is 1,024 direct ancestors.
But let's push this even further to a massive, mind-boggling number. 1 billion. How many years back do you think we'd need to go to find over 1 billion direct ancestors? If we tried to solve this just by continuing that doubling pattern, we'd be looking for the smallest value of n, where 2 to the power of n is greater than 1 billion. Now sure, you could figure this out through tedious trial and error, but let's be real, mathematicians hate tedious trial and error. We want an elegant, fast tool to solve equations for the exponent itself is the unknown. Which brings us perfectly to part 2. What are logarithms? Think of them as the ultimate translation tool, designed specifically for the exact problem we just hit. Let's completely strip away the intimidation factor right now. A logarithm is, quite simply, just another word for an index or a power. That's it. Whenever you see a logarithm, I want you to hear it asking you one very specific question. To what power must we raise the base to get this number? That is the absolute key to all of this. It's not magic, it's not impossible math, it's literally just asking you to find the exponent. Let's compare the 2 languages because it nails the concept perfectly. On one side, we have the standard language of indices, 2 to the power of 3 equals 8. On the other side, we have the exact same mathematical truth, just written in the language of logarithms, log to the base 2 of 8 equals 3. They are identically true statements. If you're ever faced with an equation like 2 to the power of x equals 12, writing it as log base 2 of 12 equals x allows you to completely isolate that unknown and solve it. It's just a perfect translation. Okay, so now that we know what they are, how do they actually behave? Welcome to part 3, the laws of logarithms, or as I like to call it, reusing the rules, because the amazing secret here is that you actually already know these rules. Here's how this builds conceptually. Because logarithms are just powers, the rules for manipulating them are completely derived from the laws of indices you probably learned years ago. Think about it. When you multiply numbers with the same base, you add their powers, right? Well, similarly, the logarithm of a product, like x times y, is equal to the log of x plus the log of y. When you divide, you subtract the powers. So the log of x divided by y is the log of x minus the log of y. And then there's my absolute favorite, the power rule. When you have the log of x to the power of n, you can pull that little n right down to the front and just multiply it. We are basically just recycling algebraic rules to make complex equations totally manageable. But before we move on to the graphing side of things, we've got to establish some fundamental boundaries to keep our math grounded in reality. First off, the base always has to be greater than 0. And because of how powers work, the curve of a logarithm only exists for positive values of x. What that means in plain English is that the logarithm of a negative number is mathematically undefined. You literally just can't do it. Also keep in mind that the log of 1 to any base is always 0, simply because anything to the power of 0 is 1. Oh, and the log of any base to itself, that's always 1. All right, part 4, exponential functions and graphs, the mathematical mirror. It's time we talk about what these numbers actually look like when we draw them out. The absolute most crucial thing to grasp here is that a logarithm is the inverse function of an exponential. If you plot the graph of y equals log base a of x, and then on the same axis you plot the exponential function y equals a to the power of x, you'll see this beautiful, kind of hidden symmetry. They are perfect mirror images of each other. They reflect cleanly right across the diagonal line where y equals x. Just swapping the x and y coordinates creates this stunning mathematical reflection. Now, if we zero in specifically on that exponential curve, like y equals a to the power of x, there are a few visual characteristics that define it every single time, without fail. First, it'll always cross the y-axis at exactly the coordinates 0, 1. Why? Because any number to the power of 0 is 1. Simple as that. Second, the x-axis acts as an asymptote. This means the curve drops down and gets closer and closer and closer to 0, but it never actually touches or crosses that line. And finally, it always has a positive gradient. It is always climbing, and as x gets larger, that climb becomes incredibly, unbelievably steep. All of this theory brings us to the ultimate question every single learner asks. Okay, but why does this actually matter? That brings us to part 5, real-world growth and decay. It's time to take our shiny new toolkit out for a spin in the real world.
Car depreciation is such a classic, perfect example of exponential decay. Say you buy a car for $20,000 and it loses 15% of its value every single year. You want to know exactly when its value will drop to half, below $10,000. So we set up our equation. Since it keeps 85% of its value, we multiply 20,000 by 0.85 to the power of n years and set that equal to 10,000. Now, how on earth do we solve for that floating n? We use our decoder ring by taking the logarithm of both sides. That awesome power rule allows us to pull the n right down into a basic multiplication problem. You just divide the log of 0.5 by the log of 0.85 and boom, n equals 4.265 years. So in roughly 4.25 years, your brand new car's value has completely halved. Let's look at another really cool example from our source material, but one that happens way faster. Fading invisible ink. Say the ink loses 1/4 of its intensity every single minute, meaning it retains 3/4 of its visibility. We need to figure out exactly when it drops below 5% readability. So we set up our inequality. 3/4 to the power of t is less than 5/100. Once again, our time t is trapped up there in the exponent. No problem. We take the log of both sides, pull that t down to the front, and solve it. You just have to be a little careful here because the log of 0.75 is a negative number. Dividing by it actually flips the inequality sign around. Do the math, and it reveals that the ink becomes completely unreadable to the naked eye after exactly 11 minutes. And logs aren't just for decay, they tame explosive growth too. Imagine you have a single biological cell, and that cell divides into 2 every 6 hours. How many cells will you have in just 1 week? Well, 1 week is 28 6-hour periods, so that's 2 to the power of 28. In just 7 short days, that one single cell has exploded into over 268 million cells. Honestly, the sheer power of the exponential function is staggering. Which actually brings us full circle to a beautiful proverb from the beginning of our source text regarding the ancestor problem. To forget one's ancestors is to be a brook without a source, a tree without a root. When we look back at our roots, mathematically speaking, the numbers absolutely explode. But as the text points out, those massive billions of ancestors couldn't have all been different people. Our family trees intersect and loop back on themselves, proving that exponential growth in reality always eventually collides with real-world limits. So, I want to leave you with this final provocative thought. We've seen just how effectively logarithms can tame the wildest exponential curves, from figuring out halving car values to calculating exploding cell divisions. But if a single biological cell, or compound interest account, or even human history can explode exponentially like that, how long is it before our own exponential population growth forces us to rethink the limits of our entire planet? It's a lot to think about. Keep questioning, keep learning, and as always, thank you so much for exploring with this explainer.